So after discussing your how to solve different physical problem using Schrodinger wave equation, let us discuss specific cases. Am I audible?
Yes,
Yes,
sir.
sir.
Is the screen visible?
Yes, sir.
So the first one is a finite potential well, and first we shall discuss bound state problem. So as shown in the screen or figure 3.3, there is three region. If your x is between minus a to a, then its value will be minus u0. And if modulus of x is greater than a, that is your in the region in the left hand side of the minus a and in the right hand side of the a, or x, the value of x is smaller than that of minus a or greater than that of a, then your u is equal to 0. And your minus u0 means your u0 is positive. So minus u0 is negative. Am I audible? Is the screen visible?
Yes, sir.
Yes, sir.
Okay. And this type of potential has sharp discontinuities at x is equal to a and minus a, and cannot correspond to real physical situations. But it can provide a very useful idealization for many real situations encountered in atomic and nuclear physics. So let us first have the Hamiltonian of this type of problem. The Hamiltonian of a particle of mass A moving in such a finite potential well is given by h cap is equal to p x cap by twice m plus u. So acting on the configuration space wave function psi, h cap takes the form minus h cross square by twice m d square by dx square plus u. And your u is a function of minus x. That is, the potential u is a symmetric function of x. U of ux is equal to u of minus x. And h cap minus x is equal to h cap x, you can see. So the Hamiltonian h cap is a symmetric function of x, as I am explained you. So the eigenvalue equation h cap psi is equal to E psi takes the form psi double dash plus twice m by h cross square multiplied by E minus u psi is equal to 0. So for bound state, E is smaller than 0, we write E is equal to minus epsilon, where epsilon is positive. So your Schrodinger equation can now be written as psi double dash minus twice m by h cross square epsilon plus u psi is equal to 0. So we now distinguish three different regions, 1, 2, and 3, which I was explaining you. In region 2, you can see the potential is U having a negative sign, and region 1 and 3, the potential is 0. So let us discuss in region 1 and 3 where the potential is 0. So if the potential is 0, then your psi 1 double dash minus k square psi dash is equal to 0, and psi 3 double dash minus k square psi 3 is equal to 0. So in the region 1, you can see the wave function is psi 1, in region 2 it is psi 2, and in region 3 it is psi 3. So we are discussing 1 and 2, so psi 1 and psi 3. So your psi 1 can be written as a1 e to the power kx plus a2 e to the power minus kx, where x is smaller than minus a. And your psi 3 is equal to b1 e to the power kx plus b2 e to the power minus kx, where your a1, a2, b1 and b2 are arbitrary constants. And the condition psi tends to 0 as x tends to plus minus infinite demands that a2 is equal to 0 and b1 is equal to 0. Then you can write a1 is equal to a and b2 is equal to b. So you can obtain psi 1 is equal to a e to the power kx, where x is smaller than minus a, and psi 3 is equal to b e to the power minus kx when psi is greater than a small a. So you can see that when x tends to plus minus infinite, psi is equal to 0. And in the region 2, that is x is between minus a to a, you have your u is equal to minus u. So if u is equal to minus u, so if your u is equal to minus u, where u0 is u is equal to minus u0, where your u0 is equal to u0 is a positive number. So your psi 2 double dash is equal to twice m by h cross square u0 minus epsilon psi 2, which is a function of x, and it is equal to 0. Similarly, you can write psi 2 double dash plus q square psi 2 is equal to 0, where q square is equal to twice m by h cross square u0 minus epsilon. And you see your q square is positive because u0 is greater than epsilon, and u0 minus epsilon is greater than 1, and your m is greater than m is positive because mass cannot be negative, and your h cross is a positive constant. So your q square is positive, and the general solution can be written as psi 2 is equal to c sin qx plus d cos qx, which I was explaining you during my discussion in mathematical physics class. So here C and D are arbitrary constants which can be evaluated by imposing the following boundary conditions. So what are the boundary conditions? Your psi is continuous across the boundary, and d psi by dx is equal to psi dash is continuous across the boundary. So you can write your psi dash at x is equal to minus a is equal to psi 1 at x is equal to minus a is equal to psi 2 at x is equal to minus a. So your psi 1 dash at x is equal to minus a is also equal to psi 2 dash at x is equal to minus a, because these are continuous, psi is continuous and its first derivative is also continuous. Similarly, your psi 2 is also continuous and its first derivative will be continuous. So you can write psi 2 at x is equal to a is equal to psi 3 at x is equal to a. Psi 2 at x is equal to minus a is equal to psi 3 at x is equal to a, and similarly your psi 2 dash at x is equal to minus a is equal to psi 3 dash at x is equal to a. So a to the power minus k can be written as minus c sin qa plus d cos qa, and your ka e to the power minus k can be written as q c multiplied by cosine of qa plus d multiplied by sine of qa. So you can get this equation by differentiating both sides of the equation, and by dividing this equation with the equation a e to the power minus k is equal to minus c sin qa plus dqa, you can have your k is equal to q multiplied by in the numerator c cosine of qa plus d sine of qa, and in the denominator d cosine of qa minus c sine of qa. And similarly you can have your b to the power minus k is equal to c sin qa plus d cos qa. Now you can differentiate both sides and you have your minus b k to the power minus k is equal to q multiplied by c cos qa minus d sin qa. And now divide this and you have your minus k is equal to q multiplied by c cosine of qa minus d sine of qa whole multiplied by c sine of qa plus d cosine of qa. Now you can solve these two and you have your cd is equal to minus cd, or cd is equal to 0. So this condition is satisfied if c is equal to 0 and d is not equal to 0. And if c is equal to 0, c is not equal to 0, then your d is equal to 0. Then solutions belonging to first class. So the first condition is what? C is equal to 0 and d is not equal to 0. So your psi 2 will be d cosine of qx, and these solutions are of even parity since psi 2 of minus x is equal to psi 2x. Similarly, the other equation will give you k is equal to q tan qa and k is equal to qa tan qa, which is a transcendental equation. And the solution belonging to second class, where c is not equal to 0 and d is equal to 0, you have your psi 2 is equal to c sine of qa and which are of odd parity, that is psi 2 minus x is equal to minus of psi 2x. And this equation will give, and the equation will give you k is equal to minus q cot qa. This is also a transcendental equation, and you can have your energy levels, and in order to find the energy eigenvalues, one has to solve the transcendental equation, and the transcendental equation is k is equal to qa tan qa. So if your this cannot hold simultaneously, as they combine to give tan square qa is equal to minus 1. So your tan qa will be I, which is a complex number, that is root over of minus a. And this equation then yield k is equal to iq, which implies that k square is negative. And this would therefore give a positive energy capital E for a bound state, which contradicts our original assumptions, that is energy E is smaller than 0. So the energy eigenvalue can be found solving this transcendental equation numerically or graphically. So the graphical method is a easier method. So let us solve it graphically, and you will enjoy solving it graphically. In order to obtain the graphical solution, we introduce two new variables. The two new variables are lambda and nu. Your lambda is equal to qa and nu is equal to k, which are positive since q and k and a are positive. And the transcendental equation take the form nu is equal to lambda tan lambda for even solutions, and mu is equal to minus lambda cot lambda is equal to lambda tan of lambda plus pi by 2 for odd solutions. So you can write lambda square plus mu square is equal to k square plus q square whole multiplied by a square, which is equal to twice m by h cross square u0 a square is equal to your k square, and is equal to your r square, where your r is equal to twice m by h cross square u0 a square root over. So root over of twice m u0 a square by h cross square, and this represents a circle of a radius r whose value is root over of twice m u0 a square by h cross square. And the even solution can be obtained by simultaneously solving the two equation mu is equal to lambda tan lambda, and your mu square plus lambda square is equal to r square. And the OR solution can be obtained by simultaneously solving the other two equations, that is mu is equal to lambda tan lambda plus pi by 2 and r is equal to twice m u0 a square by h cross square to the power half. So your r square is equal to lambda square mu square. So it may be noted that the number of solutions depend on the radius of the circle, which in turn depends on u0 a square, that is strength of potential times square of the range. For example, your u0 a square is equal to h cross square by twice m, where your lambda square plus mu square is equal to 1 square, and u0 a square is equal to 4 h cross square by twice m, where lambda square plus mu square is equal to 2 square, and u0 a square is equal to 12 h cross square by twice m, where lambda square plus mu square is equal to 3.45 square. So your lambda and mu are restricted to positive values, and your energy levels belonging to the first class can be found from the intersection in the first quadrant of the curve lambda tan lambda, which is nearly equal to lambda, with the circles of known radii. So our energy levels that belong to the second class solutions can be found from intersections in the first quadrant of the curve lambda tan lambda plus pi by 2, which is nearly equal to lambda, with the circles of known radii. And this can be plotted graphically as shown in the screen. You can see here in your x-axis there is lambda, and in your y-axis there is mu. So in the x-axis you see lambda is represented in angles, and in y-axis mu is represented by different values of r. So for r is smaller than pi by 2, or your 2m by h cross square u0 a square to the power half is smaller than pi by 2, your u0 a square smaller than pi square h cross square by 8m, there is only one bound state, that is for 0 smaller than u0 a square smaller than pi square h cross square 8m, there is one energy level belonging to first class. Okay, so you can see the dotted lines that represent mu is equal to lambda tan lambda, and you see this dotted line represents tan trigonometric function tan theta. Okay, and the point of intersection will actually the important. So for a pi by 2, smaller than or smaller than pi, or pi square by 4 smaller than 2 pi by h cross square multiplied by u0 a square smaller than pi square, or your pi square h cross square by 8m smaller than u0 a square smaller than pi square h cross square by twice m. There are two bound states, one belonging to the first class and other to the second class. And your u0 a square increases more energy levels appear successively for the even class and odd class. So the following features of the solution of the finite for the bound state of the finite well can be summarized as shown in the figure, that the bound state energy eigenvalue form a non-degenerate spectrum. This is expected for any one-dimensional bound state problem. The number of bound states is finite and depends on the dimensionless parameter r. This in turn depends on u0 a square for a given mass. The ground state is always an even state. The next bound states are alternatively odd and even states. If 0 is smaller than r is smaller equal to pi, there is one even parity bound state. If pi is smaller than r smaller than 2 pi, there are two even parity bound states. In general, there are any even parity bound states if any minus 1 multiplied by pi is smaller than r is smaller than any pi. There are no odd parity bound states for 0 smaller than r smaller equal to pi by 2. There is one odd parity bound state if pi by 2 smaller than r smaller equal to 3 pi by 2. In general, there are n0 odd parity bound states if n0 minus half multiplied by pi is smaller than r smaller equal to n0 plus half multiplied by pi. Okay, so let us discuss the nature of eigenfunctions. The eigenfunctions are similar to those of infinitely deep potential well, but they penetrate slightly into the classically forbidden region where they decay to zero exponentially as shown in figure 3.5. So you can see the even solutions in the left hand side and the odd solution in the right hand side. So in the even solutions are symmetric so in reference to your y-axis, and odd solutions are antisymmetric with reference to the y-axis. Okay, am I audible?
Yes, sir.
Yes, sir. If you have the infinitely deep well, you expect that in a limiting case of u0 tends to infinite. So if you're infinitely deep well, you can see in the screen, if it is infinitely deep, so your u0 will not be a finite number. u0 will be infinite. If it will be infinitely deep, then your u0 will be infinite in region 2 and where the wave function is psi 2. And your in the region 1 and 3, psi 1 and or psi 3, u0 is equal to 0. And in the region 2, u0 is equal to infinite. So if you put u0 is equal to infinite, you will have your solution for infinitely deep well. The result of the infinitely deep well should be obtained, and as u0 tends to infinite, r tends to infinite. You see here, if u0 tends to infinite, what is the expression for r? You see here, the expression for r is 2m u0 a square by h cross square root over. So if u0 is equal to infinite, then your twice a square by h cross square multiplied by infinite root and root over of that will be what? Infinite. And the allied values of mu are mu n is equal to n pi by 2, where n is equal to 1, 2, 3, so on and so forth. And your energy eigenvalue En will be h cross square pi square by 8m square whole multiplied by n square. So there is an example where you can have a better understanding of the problem. An electron in a finite one-dimensional square well of depth u0 is equal to 10 electron volt and width 2a is equal to 2 angstrom. How many bound states are possible? You see, your u0 is equal to 10 electron volt. That is 1.6 into 10 to the power minus 18 joule, because 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. And your A is equal to 1 angstrom. Since 2A is equal to 2 angstrom. And 1 angstrom, you know, is equal to 10 to the power minus 10 meter. So your U0 A square will be 1.6 into 10 to the power minus 38 joule multiplied by meter square. So for electrons, your H cross square pi square by 8m is equal to 1.49 into 10 to the power minus 38 joule multiplied by meter square. By putting the values of H cross pi is equal to 3.14 and m is equal to your 9.1 into 10 to the power minus 31 kg, that is the mass of the electron. So for H cross square, pi square by twice m is equal to 5 into 5.96 into 10 to the minus 38 joule meter square. So you know that H cross square pi square by 8m is smaller equal to U0 A square is smaller is equal to H cross square pi square by twice m. So there are only two bound states for the electron in the square well. Are you getting it? So your H cross square pi square twice m is equal to 5.96 into 10 to the power minus 38 joule meter square. Your pi H cross square pi square by 8m is equal to 1.49 into 10 to the power minus 38 joule per meter square. So your U0 A square is in between these two, 1.49 into 10 to the power minus 38 joule per joule multiplied by meter square and 5.96 into 10 to the power minus 38 joule multiplied by meter square. So their possible bound state are only two. Okay. Then your linear harmonic oscillator, which is also known as simple harmonic oscillator. Am I audible?
Yes, sir.
Yes,
So
sir.
linear harmonic oscillator or simple harmonic oscillator is a point particle attracted towards a fixed center by a force proportional to the displacement of the particle from the fixed center. So if the motion is chosen along x-axis or one-dimensional, then the origin at the force center, then the force is given by F vector is equal to minus k multiplied by x vector, which is equal to minus x cap multiplied by du by dx, where k is the force constant and u is the potential energy function. So u can be written as half kx square is equal to half m omega square x square, where k is equal to m omega square. And your m is mass of the oscillating particle and omega is the angular frequency of the oscillation. So we can note that u is equal to u of x is equal to u of minus x, and it is a symmetry function as shown in figure 3.6. And the potential energy function is also continuous function of x, and the plot of u versus x is shown as in the screen. So here your Hamiltonian of the oscillating particle h cap is equal to p cap square by twice m plus half m omega square x cap square, and it has the property h cap of minus x is equal to h cap of x because it is a symmetric function about y axis. So the Hamiltonian for the oscillator is a symmetric function of x, and the time independent Schrodinger equation for the oscillator is minus h cross square by twice m d square psi by dx square plus half m omega square x square psi is equal to E psi. And your energy value equation and its solution can be obtained as follows. The energy value equation h cap psi is equal to E psi for the oscillator takes the form psi double dash plus twice m by h cross square multiplied by E minus half m omega square x square psi is equal to 0. And your psi double dash is plus twice m E by h cross square plus m square omega square x square by h cross square psi x is equal to 0. And the eigenvalues and eigenfunctions of the oscillator can be obtained by solving the equation. In order to achieve this, we introduce a dimensionless parameter variable y, which is equal to n omega by h cross to the power half multiplied by x. And your d by dx is equal to dy by dx multiplied by d by dy, which is nothing but m omega square by h cross square root over or to the power half d by dy. So your d square by dx square can be written as d by dx of d by dx, which is equal to m omega by h cross square d square by dy square. Now by substituting these into the equation psi double dash plus twice m e by h cross square minus m square omega square x square by h cross square psi is equal to 0, we have m omega by h cross multiplied by psi double dash, which is a function of y, plus twice e by h cross omega minus y square psi is equal to 0. So you know m is equal to positive, omega is equal to non-zero, and h cross is also positive. So your m omega by h cross is not equal to 0. So the eigenvalue equation reduces to psi double dash plus lambda minus y square psi is equal to 0, where lambda is equal to 2e by h cross omega. Now you can see the asymptotic behavior of psi, which is a function of y. So as y tends to infinite, you can see y square is very, very greater than lambda. And for any finite value of e, the dimensionless variable lambda is negligible in comparison with y square. So this equation reduces to psi infinite double dash minus y square psi infinite is equal to 0. And psi infinite is equal to e to the power beta y square, be a trial solution of this equation, and your psi infinite dash is equal to 2 beta y e to the power beta y square, and psi infinite double dash, or this is second derivative of psi infinite with respect to y, is equal to 2 beta e to the power beta y square multiplied by 1 plus 2 beta y square, which is nearly equal to 4 beta square y square e to the power beta y square. So this equation, your y infinite double dash minus y square y infinite is equal to 0 becomes 4 beta square minus y multiplied by y square e to the power beta y square is equal to 0, where your 4 beta square minus 1 is equal to 0, or beta is equal to plus minus half. So your psi infinite is nearly equal to e to the power plus minus half y square, and the solution must be finite everywhere and satisfy psi infinite tends to 0 as y tends to plus minus infinite. But the solution with positive exponent psi infinite nearly equal to e to the power minus e to the power half y square diverges as y tends to infinite, and it is not acceptable. So the general acceptable solution is of the form psi is equal to f multiplied by e to the power minus y square by 2, where f is to be determined. The function f should be such that it does not affect the asymptotic behavior of psi. So let us write the equation. Your psi dash is equal to f dash minus y f whole multiplied by e to the power minus y square by 2 is equal to 0. So you can simplify it and write f double dash minus 2y f dash plus lambda minus 1 f is equal to 0, because e to the power minus y square by 2 is non-zero. So the power series solution, which I have told you in the mathematical physics class of this semester, to solve this type of equation having variable coefficient, you can see that the coefficient of f dash is equal to minus 2i, which is a variable, which is variable. So for this type of solution, the Frobenius method or extended power series method is used, and also power series method is very much important. So here we solve it by power series method. So you can see, so when we solve it by power series method, so you have to write Fi as this form, that is summation s is equal to 0 to infinite as y to the power s, and f dash is equal to summation s is equal to 1 to infinite as y to the power s minus 1, because the differentiation of x to the power n is equal to n x to the power n minus 1. Similarly, your f double dash is equal to summation s is equal to 2 to infinite s into s minus 1 as y to the power s minus 2. So this is the three terms, and by putting it in your differential equation, that is f double dash minus 2i f dash plus lambda minus 1f is equal to 0, you have your summation s is equal to 2 to infinite s into s minus 1 as y to the power s minus 2 minus 2 multiplied by summation s is equal to 1 to infinite s as y to the power s plus lambda minus 1 multiplied by summation s is equal to 0 to infinite as y to the power s is equal to 0. So to solve it, we have two things to remember. The coefficient of lowest power will give you the initial equation from which you have the roots of the equation, and the coefficient of the highest power will give you the recursion relation which will give you the solution. So you can see y to the power s minus 2 is the coefficient, is the lowest power in the equation, lowest power of y in the equation. So summation s is equal to 2 to infinite s into s minus 1 s is the initial equation, and from there you can have your value of s. Similarly, the coefficient of the highest power, that is y to the power s, is equal to lambda minus 1 summation s is equal to 0 to infinite s. This will form the recursion relation, and by using the power series you can have the solution, and you can go through my notes as so which I will circulate you, and I am also explained you in detail during my mathematical physics class how to solve a power series solution when you have the initial equation and the recursion relation. You can see that your s plus 1 into s plus 2, a s plus 2 minus 2s plus 1 minus lambda s is equal to 0. So a s plus 2 is equal to 2s plus 1 minus lambda by s plus 1 into s plus 2 as. And this is the recursion relation which I was telling you. So by expanding e to the power y square into power series, you have this type of equation where your bs is equal to 1 by s by 2 factorial, and bs plus 2 is equal to 1 by half s plus 1 factorial. So bs plus 2 by bs is equal to 1 by half s plus 1, which is nearly equal to 2 by s for large s. So if s is very large, f5 behaves as e to the power y square, and psi will be nearly equal to e to the power minus y square by 2 multiplied by e to the power y square, which is equal to e to the power y square by 2. So the series terminates at the nth term, and your an is not equal to 0, and your an plus 1 is equal to 0, and an plus 4 is equal to 0. So now your 0 is equal to 2n plus 1 minus lambda by n plus 1 into n plus 2 whole multiplied by n. So your lambda will be 2n plus 1, and which putting in the equation you have your recursion relation as I have told you earlier. So your lambda is equal to 2n plus 1, where n is equal to 0, 1, 2, so on and so forth, and n is equal to n plus half h cross omega, where n is equal to 0, 1, 2, so on and so forth. This gives the energy eigenvalue of the oscillator, and your E0 will be half h cross omega, E1 will be 1 plus half multiplied by h cross omega is equal to 3 by 2 h cross omega, E2 will be 5 by 2 h cross omega, 2 plus half multiplied by h cross omega is equal to 5 by 2 h cross omega, so on and so forth. You can see if you subtract E1 and E2, your 3 by 2 minus half is equal to how much? 3 minus 1 by 2 is equal to 2 by 2 is equal to 1, that is h cross omega. If you subtract E2 to E1, then 5 by 2 minus 3 by 2 multiplied by h cross omega will give you 2 by 2 h cross omega is equal to h cross omega. So En minus 1 will give you h cross omega for all n. That means the energy values are equispaced. And they are discrete. Then eigenfunctions. So your lambda is equal to 2n plus 1. So your f double dash minus 2y f dash plus 2n f is equal to 0. So your fy is equal to hny is equal to minus 1 to the power n e to the power y square d to the power n by dy to the power n e to the power minus y square. And I have told you that this is Hermite polynomial during my mathematical physics class. So we satisfy the recursion relation hn plus 2 is equal to 2y hn plus 1 minus 2n plus 1 hn. And the orthonormality condition, as I told you in my mathematical physics class during your Hermite differential equation, integration minus infinite to infinite hn hm e to the power minus y square dy is equal to 2n multiplied by n factorial root over of pi del mn. Okay, so the eigenfunction of the harmonic oscillator are therefore expressed as psi n is equal to an hn e to the power minus y square by 2, and your psi n is equal to an hn alpha n to the power alpha n hn is a function of alpha n multiplied by e to the power minus half alpha square your n square x square. So your alpha is equal to root over m omega by h cross, and your y is equal to alpha x, and an are y and an are normalization constants. So which are determined by using the normalization condition, that is 1 is equal to minus infinite to infinite psi n star psi n dx, and your n will be estimated as alpha by 2 to the power n factorial root over pi to the power half, and the energy eigenfunctions for harmonic oscillator will be psi n, which is a function of x, is equal to root over of alpha by 2 n factorial root over of pi whole multiplied by hn e to the power minus alpha square x square by 2, where hn is the Hermite polynomial. And you know, and I have told you and shown you how from the Hermite differential solution of Hermite differential equation, the Hermite polynomial h0, h1, h2, and h3 are evaluated. And you know h0 is equal to 1, h1 is equal to 2y, h2 is equal to 4y square minus 2, and h3 is equal to 8 y square minus 12y. So by putting these, you have your eigenfunctions corresponding to n is equal to 0, 1, 2, 3 states. Your psi 0 is equal to alpha by root over pi to the power of half, you multiplied by e to the power minus alpha square x square by 2. Psi 1 is equal to alpha by 2 root over pi to the power half, 2 alpha x e to the power minus alpha square x square by 2. Psi 2 is equal to alpha by 8 root over pi to the power half, 4 pi square alpha square minus 2 whole multiplied by e to the power minus alpha square x square by 2, and psi 3 is equal to alpha by 48 root over pi square to the power half, 8 alpha q x q minus 12 alpha x whole multiplied by e to the power minus alpha square x square by 2. And the energy level diagrams are shown in the figure 3.7. You see that E0 is equal to half h cross omega, E1 is equal to 3 by 2 h cross omega, E3 is equal to 5 by 2 h cross omega, E2, E3 is equal to 7 by 2 h cross omega, E4 is equal to 9 by 2 h cross omega. So what do we get from this? The first thing is the energy levels are equispaced, and the difference is your h cross omega. And the other important fact you can see, your u0 is equal to half h cross omega. So the ground state or the minimum energy state has a non-zero value. So and the value is half h cross omega. So it is called the lowest value of energy level possible in a simple harmonic oscillator. And since it is non-zero, so we can say it 0 point energy. We can call it a 0 point energy. Is the screen visible or not?
No, sir.
No,
तो क्या
sir.
No,
बोले
sir.
नहीं बोले से दिख नहीं रहा है और मैं क्या आपको बता रहा हूँ यू हैव टू से ना just wait I am again presenting it maybe due to network problem this might कितने समय से दिख नहीं रहा है
2 मिनट हुआ है सर.
अच्छा अच्छा ठीक है कोई बात नहीं मैं उसको 2 मिनट फिर उसको दिखा देता हूँ slow network there in the desktop चला गया Network. So when the internet is restored in the desktop, we will have there for the timing. I am showing it from here. Is it visible now?
Yes, sir.
Yes, sir.
So let us have it till the internet is restored in the desktop. So I think from the here the screen is disappeared or from somewhere else. Here or from here. Please see this slide. Huh? Anybody? Or this slide? Or this slide? This slide?
This, sir.
Okay. So you see that psi n can be represented as alpha by 2 to the power n factorial root over 5 whole to the power minus half hn e to the power minus alpha square x square by 2. So you can see that h0 is equal to 1, h1 is equal to 2y, h2 is equal to 4y square minus 2, h3 is equal to 8y square minus 12y. These are Hermite polynomials. By putting these values in the expression for psi n as shown in 3.59, your psi 0 can be written as alpha by root over pi to the power half e to the power minus alpha square x square by 2. Psi 1 can be written as root over alpha by 2 root over pi multiplied by 2 alpha x e to the power minus alpha square x square by 2. And your psi 2 can be written as alpha by 8 root over pi to the power half multiplied by 4 alpha square x square minus 2 multiplied by e to the power alpha square x square by 2, and your psi 3 can be written as root over of alpha by 48 root over 5 multiplied by 8 alpha q x cube minus 12 alpha x whole multiplied by e to the power minus alpha square x square by 2. And you can see the energy level diagram in the screen, figure 3.2. Your E0 is equal to half h cross omega, E1 is equal to 3 by 2 h cross omega, E2 is equal to 5 by 2 h cross omega, E3 is equal to 7 by 2 h cross omega, E4 is equal to 9 by 2 h cross omega. So your energy levels are equispaced, that is h cross omega. And you can see the lowest energy level E0 is non-zero. It is having value half h cross omega. So this is called 0 point energy. 0 at which the energy has some value and non-zero value. This is called 0 point energy. E0 is called 0 point energy and its value is half h cross omega. Okay. Then they are equispaced. And you can see also that del En by En is equal to 2 by 2n plus 1 is equal to 1 by n plus half. And your, if n is very, very large, your del En by En is nearly equal to 1 by n. So your n tends to infinite, your del En tends to infinite, and this implies that states with large n are separated by intervals that is small compared to the total energy of those states, and a classical result is thus approached. Similarly, the existence of 0 point energy implies that the particle in the oscillator well cannot at rest at the equilibrium position. The 0 point energy can be shown as a necessary consequence of uncertainty principle. Am I audible?
Yes, sir.
Is the screen visible?
Yes, sir.
Okay. Now let us discuss the energy eigenfunctions. You can see the value of psi 0, psi 1, psi 2, psi 3, and I have explained it earlier, where E0 for psi 0, E0 is equal to half h cross omega, for psi 1, E1 is equal to 3 by 2 h cross omega, so on and so forth. And you can see that psi of minus x is equal to psi of x. So your psi n of minus x is equal to psi n of x, which n is even. And if n is odd, your psi n of minus x is equal to minus psi n x. Okay, so the eigenfunction of the harmonic oscillator are have of a definite parity. So even parity and odd parity. So you can see here in the screen that the ground state wave function psi 0 has nodes, and it is a Gaussian function of x, and it is the excited fast excited state psi 1 has one node. You can see in the screen the fast excited state has one node. Similarly, second excited state psi 2 has two nodes, so on and so forth. And your n state has n nodes. So energy levels, wave function psi and their probability density psi square for the first four states are presented in the first figure and second figure respectively, and the intersection of probability curve with the potential curve u gives the finite probability of observing the particle outside the classical limit of oscillator, and the probability density for harmonic oscillator is shown in the third figure as in the screen. So first one is the psi and second one is psi square or probability. Okay, so there are some worked out examples which you can try, and you will understand how physics is being realized in simple harmonic oscillator. This I have told you yesterday for spherical polar coordinate system, how we can solve the Schrodinger wave equation, and this will be very helpful in solving the hydrogen atom problem. ओके
सर
जी सर बताइए।
सर ये पीडीएफ सेंड कर दीजिए ग्रुप में।
हाँ कर देंगे। और क्या डाउट है बताइए।
सर पढ़ने के बाद पूछेंगे।
ठीक है। So this is hydrogen atom, NLM. This represent 4s state, and the eigenfunction psi 100 is equal to 1 by root over pi z by a0 square to the power 3 by 2 e to the power minus zr by a0. R for n is equal to 2, L is equal to 0, M is equal to 0. Your 2s state. So the wave function psi 2 to can be represented as shown in the screen. Similarly, for n is equal to 2, L is equal to 1, M is equal to 0, that is 2p state. For n is equal to 2, L is equal to 1, M is equal to 1, that is also 2p state. And psi 2 1 0 and psi 2 1 1 is shown in the screen. And the wave function are solved by using spherical polar coordinate system psi NL psi NLR, which is a function of r theta phi, can be written as root over of 2z by n a0 to the q multiplied by n minus L minus 1 by 2n, your multiplied by n minus L factorial q whole multiplied e to the power minus your z r by n a square multiplied by 2z r by n a0 to the power n plus L so subscript and 2L plus 1 superscript whole multiplied by 2z r by n q0 whole multiplied by Lm, which is a function of theta and phi. And the quantum numbers are realized from this equation, and the 4 quantum numbers are described, which you have already know. The quantum number n, principal quantum number, then the quantum number L, quantum number L, which can be realized as L vector modulus is equal to L into L plus 1 to the power half h cross. Okay, so here you can have your SP, D, F, G, H states, and your for different L values in tabular form, different N values, the values of L what can be realized are shown in the screen. Similarly, quantum number M or magnetic quantum number is realized from this equation, and degree of degeneration of hydrogen atom are as shown in the screen, that is Gn is equal to 2 into n minus 1 into n by 2 plus 1, and Gn is equal to n square. So the nth level is n square fold degenerate, and n square eigenfunctions corresponding to the given En. And your En is equal to minus mu e to the power 4 by 8 E0 square h cross square whole multiplied by 1 by n square is equal to minus 13.6 by n square electron volt. Okay. So here you can see that the energy levels are not equispaced, and n is equal to 1 level is non-degenerate, and so on and so forth. And your n is equal to 2 is 4-fold degenerate, n is equal to 3 is 9-fold degenerate, and so on and so forth. And you can see in the screen the story of a hydrogen atom from E1 to continuum energy. And here are some worked out examples which you can try. Any other doubt? You can go through it, and I shall address your doubts if you have any. So let us have a 7 days break, and after that we have another class at this time 6 p.m. So there you can have the things which you want to ask me, or you want to tomorrow also a class, because actually for 8 classes I think already completed. Anybody?
Sir, MPH-4 all courses are over?
I think over, but you can also to check.
Okay, sir.
Okay.
Sir, have you
Because
sent me
I have
PDF?
explained you Dirac delta function and other things, and Dirac Heisenberg picture and Schrodinger picture side by side. Today I have explained you the problems in Schrodinger formalism, and same case will be there in your physics will be same in the Heisenberg formalism, only the mathematics is different, and I have explained you how you can have your mathematics in the Dirac bracket notation and your Heisenberg formalism. So you can try it. Okay. If you
Sir,
think that some
MPH-4 not
portion is being skipped, then in the class, in the next class, which I think will be on next Wednesday, you can ask them.
next Wednesday we will have.
Because for 7 days you go through this, and after that,
Okay.
if we meet, then you might have some idea or some thing which you communicate me that some portion is not, if not covered, then we shall
Sir,
cover
can
that
you,
on that day. If all the portions are covered, then we shall have discussion in the things we have discussed already.
sir, can you give us some important question related to exam?
So actually, I shall I can give you the previous year question paper. From there, you can have your
I have
selections.
Sir, we have previous year question paper. We know the
From that you
pattern,
can
but
see, that you can see that which type of questions are being asked in the exam, and from there you can have your selections. Because
okay,
in
sir.
multiple types of question there is some might be some difficulties, but for long type question and other questions, I think you definitely have better selection and you might have better results. So you have your selections. If you total your 15 questions will be asked, then I think 25 question if you prepare, then out of them 15 question you will answer. If 20 question you can prepare, then out of that you can attempt 12 to 13 question very effectively, or not.
So
So
if
that
you
you
will
can,
provide us so that we can prepare those questions. Actually, we
see,
are not getting any
this
questions.
will be problematic, because if I have some, I shall give you some selection, then that part is also part of your, that is part of your exercise, because having a selection is also very important. So when you sit in the exam, so you
Yes.
yourself try. That is your
Okay,
one
sir.
of the your task, and you learn from it.
So
क्योंकि
as we are
आजकल
doing
जितना
a
भी हुआ है,
distance
टीचर
course,
का भी दिया है क्या सिलेक्शन? आप लोग खुद करके इतने तक आ चुके हैं एमएससी तक, या बीएससी में टीचर
no,
देते थे
sir.
सिलेक्शन?
Distance, as it is a distance course, so we are facing a problem. That's why we are
No,
asking some
problem is that
important.
you do not have much classes. But if you
Yes, sir.
identified the selections, and we shall discuss those selections very rigorously in our next class. Okay.
From previous year question, we can know the pattern, but some
Not in
selective
the pattern.
question.
From the previous year question, to 2 3 year question, you can have the
Yes.
questions also.
No, we don't have 2 3 question. We are this physics has been started from July 24. So
Okay,
only
so
two
that
years
is a
of
problem.
question we have.
So I think the questions, what can I say officially? Officially, I cannot say
Okay, sir, we
anything.
will see that. Okay,
Unofficial, I
sir.
can
Okay.
say something.
Okay, sir. All right.
Officially, you can also not say something when you will be a teacher.
Okay, sir.
ठीक है?
Sir, MPH-4 notes have you given to me anything?
No, I told you that after completion I shall give. So it was not being
Sir,
completed. So I could
MPH-1 you have given all PDF.
I shall give you all the course materials. Yes, tomorrow.
Okay, sir. MPH-1 or
Okay.
MPH-4?
Both. MPH-1 तो मैंने सारा दे दिया था शायद.
Yes, sir. I'm asking that because last two class I was absent. That's why I
मैं
don't know when this
MPH-4
four
का
class
कुछ भी
was.
नहीं दिया.
Okay,
One का
sir.
तो I think everything I have uh,
The
given.
MPH-1 last PDF you have given me, that was of. Let me check.
वन का अगर कुछ नहीं है तो मुझे टेक्स्ट कर दो कौन सा पर्सन मैंने नहीं दिया है. ठीक है.
MPH-1
But
last
I
PDF
think
you have
I have
sent that
given
was.
all the course material, because there are something which needs note. So for those materials, I have made some note and circulated. And where there is no note is required, you can go through the. So for example, you need to understand power series and Frobenius method, and you have some
Sir,
examples. And
sir,
from
on
that, you
last
can have
Saturday.
also other problems. So which is essential. I have given those notes, and whether I
Yes,
have not given note and you give you the course material, because those are your own task to solve those things so that you can learn something. So I think majority
sir,
of the thing which needs detailed derivation and understanding of the multiple steps, I have given all those notes.
sir, on last Saturday you have sent me one PDF that is of 68 pages. That was MPH-1 or MPH-4?
I have not recollected. MPH-4 का मैंने कुछ नहीं दिया है सर.
Okay, sir.
MPH-1 का
So
मैंने सारे दे दिया
MPH-1.
है.
Okay,
अगर
sir. So
MPH-1 का मैं
MPH.
क्वांटम का फास्ट पार्ट दिया होगा मुझे कोई याद नहीं. श्रोडिंगर पिक्चर अगर दिया होगा, let me
Mm-hmm.
check.
So that
ठीक है,
was
अगर नहीं
unit
दिया
1
होगा तो I shall
matrices and the
circulate tomorrow.
operations.
I shall cross check and so supply the course material which I have not given.
सर जो पीडीएफ आपने भेजा था सैटरडे को वो यूनिट 1 मैट्रिसेस एंड देयर ऑपरेशन था वो
Now that
हेडिंग
is
है
your
वो.
mathematical physics.
ओके सर दैट इज द लास्ट पीडीएफ ऑफ एमपीएच 1.
हाँ, मैं इसलिए बोला ना MTH-1 का मैंने दिया है, MTH-4 का मैंने कुछ नहीं दिया अभी तक.
Okay, sir. So will you provide it today or any
Tomorrow I
other
shall
day?
provide.
Okay, sir.
Okay. Any other question from any other students or participants?
सर जो भी पीडीएफ आप डिस्कस कर रहे हो थोड़ा भेज देते तो वहीं से ही देखेंगे हम.
नहीं, मैं पहले क्यों नहीं दे रहा हूँ, पीडीएफ भेज दूंगा तो यू विल बी एब्सेंट माइंडेड ड्यूरिंग द क्लास.
नहीं
I
अपने
think
पढ़ाने के
I
बाद
may be
पूरा
wrong.
सेंड कर.
I may be wrong, but I think so. Hence, I have circulated after completion.
Yes sir, after completion only provide all the PDF.
मैं अभी दे दूंगा ना, इसलिए बोला कल, क्योंकि क्वांटम कंप्लीट हो गया मुझे लग रहा है.
Yes sir. So tomorrow will you have any class or after 7 days?
If you say tomorrow you have need a class, I shall take, because I think more than 8 period I have taken.
No, if
No.
MPH-4 has been completed, then we don't need any class. We will see the PDF and we'll
हाँ.
practice from there. If you have any doubt, I will say you will take
If
the class.
you think that some portion is being skipped, then you can text me tomorrow.
Yes sir.
You check and text me.
So
Okay.
MPH-4 is completed totally.
I think completed, but you also cross check.
Okay sir.
Other any participant? Any other question?
No, sir, we'll read that PDF. Then any doubts, sir, we'll then after that we'll inform, sir.
ठीक है.
Yes.
Or anybody else? ठीक है. So you also have a Google online meeting among yourselves. So I think 20 participants you are regularly attending classes. You mark those phone numbers from this Google Meet and you form a group, and among yourself you can discuss and chalk out the selection which you are asking for. Okay.
Yes sir.
आप लोग बैठ
Okay
जाइए
sir.
ना, जो रेगुलरली क्लास आ रहे हैं. ठीक है. Yes, previous year it was difficult, as per your information, that it was the first batch, but this year you have the previous year question, so you have a format and you know how the question setter set the next year question if you have the first year question. Am I right or wrong? आपको पता है, आप बीएससी तक आ गए तो ऑनर्स पढ़ के आपको पता नहीं. ओके.
Okay, sir.
Okay sir.
Okay, okay, sir.
ठीक है. So thank you all and best of luck for your exam. And next
Tomorrow-
Wednesday we shall
Sir,
meet
tomorrow
at
who will
6.
take the class? Sir, tomorrow who will take the class? Do you know that?
आपका जो होगा आपका देख लेते
सर वो तो
हैं.
आपका भी क्लास है
मेरा है, लेकिन
4
मेरा
से
सैटरडे
5
संडे नहीं था ना, मैंने 4 क्लास ले लिया.
हाँ हाँ.
सैटरडे
Okay
संडे
sir, I will ask you.
सैटरडे संडे मैंने 4 क्लास ले लिया. और कितना दिन बचा है? You see that my class
Only
was
7
from
7.
रुको 1 मिनट में देख लेता हूँ. My class was from my class was quantum mechanics class from 17th 17 नहीं, ये शुरू हुआ क्वांटम मैकेनिक्स 11 तारीख को. ठीक है. ये था
Yes, sir.
11, 11th, 14th, 15th, 17th, 21 and 21 and 22 and 23, 24. ठीक है. तो कितना
Yes,
हो गया?
sir.
1 2 3 4 5 6 7 8 क्लास था नहीं.
Yes sir.
सो आपका नहीं था 12 एंड 13. 12 13 को मैंने 4 क्लास लिया है. हमें
हाँ,
राइट
हाँ.
हो या 3 क्लास लिया?
Yes, sir.
4 या 3
हाँ सर,
क्लास
अब बीच में
हो
तो
गया.
क्लास लिए थे. कितना क्लास मन
मैंने
क्या
3-4 क्लास ले लिया उसमें. आज कितना तारीख है? आज शायद 16 है. आज क्लास नहीं था. 15
नो
था, आज
आज क्लास
16 को क्लास नहीं था. तो इसके बाद बच्चा है ये 20 20 21 22 23 24. तो आज का एक क्लास हो गया. बीच में मैंने 4 क्लास लिया है. 5 क्लास हो गया ना.
यस सर.
तो आपका और 4 क्लास बचा है और मैंने 5 क्लास ऑलरेडी ले चुका हूँ.
यस सर, आई विल टेल टू अदर सर टू टेक द क्लास.
क्योंकि वो दिन जो नहीं आए उस दिन, तो बड़े सारे बच्चे तो आए थे उस 2 दिन.
हाँ, विवेक सर थोड़ा क्लास ले अच्छा होगा. वो बहुत ही कम क्लास लिए हैं. मतलब
उनके पास आ
कोर्स
जाएगा
ओवर हो
फिर।
गया था, थोड़ा डिस्कशन
सर
क्लास
विल
हो रहा
कम ऑन 21st 22nd एंड सो ऑन सो फोर्थ। और उनका भी है 29th, और उनका है, और का है ना आपका जो दिया है
है। हाँ हाँ,
टाइम
गणेश और
टेबल में,
मैथ्स।
उनका आगे क्लास है, मेरा और नहीं है, मेरा खत्म हो गया। तो आई
हाँ सर,
शैल
ठीक।
have it on next Wednesday. Already I have taken 9 classes, I think.
यस सर।
So I have been assigned 8 classes only. So another
ओके
1 class में ले लूंगा, 10 क्लास हो जाएगा, ठीक है।
ओके सर।
10 क्लास
सर व्हेन यू विल टेक दैट क्लास?
वेडनेसडे 7 दिन आपको दे दिया गया, या फिर मंडे, आप जब बोलेंगे।
सर वी विल डिस्कस एंड टेल यू लेटर।
यू मैसेज मी, ओके,
यस।
ठीक है। थैंक यू ऑल। एनीबडी एल्स,
थैंक
एनी
यू
डाउट?
सर।
So thank you.
थैंक यू
Thank
सर।
you, sir.
Thank you, sir.
थैंक यू सर।